Hi everyone. Today we will continue discussing our topics in magnetics. Last class we stopped at this point here, example 1.3. So let me just refresh your knowledge again. What we are discussing is magnetic circuit and convert magnetic circuit into electrical circuit or equivalent electrical circuit, and then start analyzing these circuits. So we solved two examples last session for a certain circuit of a relay, and we mentioned that relay is one of the applications of magnetic circuits we used in industry. It's used in control and in circuit breakers for protection and control as well. So here we have another circuit or another magnetic circuit. It could be used in other applications. So let's see together what we have in this example. So in this example here, guys, in the magnetic circuit of the figure below, the relative permeability of the ferromagnetic material is 1200. So this is mu R of our magnetic material used in this magnetic circuit. So most probably if the mu R is given, guys, the curve, the BH curve will not be given. So if the relative permeability is given in an example, you may not have or you may not need the BH curve, since we assume that the permeability is fixed number. Okay? Because as we mentioned before, according to the BH curve for any material, it will have like linear part and knee part, then saturation part. So the permeability is different for each interval. However, if the mu R is given in an example, so this means the curve will not be given, and we assume the permeability is going to be constant in this case. So just to remind you about what we have discussed in previous classes. Okay, now, neglect magnetic leakage. What's the meaning of magnetic leakage? This is very important, guys. And fringing. So we mentioned before, guys, if you have flux moving between the air gap and core, we expect to have fringing. So fringing means the cross-section area will be different. So instead of having straight lines of flux moving between the core and air gap, you may have some like parabolic path for the flux lines. So this is called fringing. And here in the example, he says neglect magnetic leakage and fringing. This is actually what we are doing most of the time in our questions, because all of the time we consider that area of air gap equals the area of our core. So we are already assumed that in our problems. Also, he says here all dimensions are in centimeters. So we have here all dimensions given on this diagram. So 2 here means 2 centimeters, 50 means 50 centimeters, and so on. So these are dimensions for the length of the magnetic path. So you can calculate the magnetic path length by means of these numbers. Okay. Also, the cross-section area should be given somewhere. We will see if it is mentioned here. So all dimensions are given or are in centimeters, and the magnetic material has a square cross-section area. Okay, so squared cross-section area means if we have a section here like that, you will find that the material is square. And if the material is square, what would be the dimension? So if this is the width of the cross-section area, which is in the direction perpendicular to the screen. So this is going to be the length of the section, which is given already here. So since this is 2 centimeters, so the depth is also 2 centimeters. So we can say from here, the cross-section area is 4 square centimeters, which is 4 times 10 to power minus 4 square meters. So this is the cross-section area of our magnetic core. What is needed here in this question? Determine the air gap flux. So he needs to calculate the magnetic flux in the air gap. So let's say phi g. The air gap flux density. So flux density is B, so Bg. And the magnetic flux intensity in the air gap, and Hg. So we need to get all air gap flux, flux density, and flux intensity. Nice. First step is, let's firstly delete the lines that I have here. Sorry. First step is we need to convert our magnetic circuit into equivalent electrical circuit. As you can see, guys, we have here two sources of flux. The first one in the left arm, it has a certain coil of 500 turns and the current is 10 ampere. And we have another coil here of another 500 turns. And if you have a look, you will find that the current of the first coil is moving and connected to the second coil. So firstly, we need to observe the current and the flux direction. Consider the right-hand rule we described before. So if this current, firstly, the current is coming like that. Current is moving like that here. So this is the current direction here, and this is the current direction given here. So for the current direction of the left-hand side coil, what is the flux direction? So if you apply the right-hand rule for the current here on the first wire, you will find that the flux is moving in this direction from out of core and return back in the opposite direction in the core. So this means the flux is moving up in this direction. Check the other side. So the current is coming from the back wire and return here to the front wire. So let's see from the front wire on the top, you will find that the current is flowing such that making flux rotating like that as well, which means still the flux here is moving towards the top. So this is the flux direction now coming from both of coils. For that, we can say this is the first source of flux, and the flux direction of the first source is moving in this direction, and this is the other source, and the flux source is moving in the flux direction is in counterclockwise. So this is clockwise and this is counterclockwise direction, and both of fluxes now will be collected together. So this flux from the left hand side, from the left arm, will move in this direction. This right arm will move also, the flux is moving in this direction, and there will be collected together and move in the direction to the lower part, and then started again to be distributed to the left and right arms. So this is the flux rotation or flow in this magnetic core. Now, we need to make the reluctances of our core and air gap. If you consider the dimensions here, you will find that we have a symmetry for the core, for the left part and the right part. So let's say this is C shape. So we have here C shape to the left and another C shape to the right. And then we have I shape in the middle. And the I shape has a part of air gap in between. So we can see that the dimension of C shapes are identical, which means we have symmetry for the reluctances in our core. Why? As you can see, the distance from this point to that point is 50. The same is here. The same is for the lower parts. And also here we have the same dimension. So this means, guys, the core is symmetrical around the central arm. So we can say now, or we can make now many paths for our reluctances. So we can consider that we have a reluctance for this part starting from B, from letter B here, from point B. So we have B, A, F, E. So this is a left C shape. So we have a first reluctance of reluctance BAFE. And it will be identical to another reluctance of the C shape in the right-hand side, which is BCDE. So we call it by these letters, guys, which is the same length or average length of our magnetic flux. This is the average length of the magnetic flux path. So we have now RBAFE and RBCDE. Another part of the reluctance of the I shape in the middle, we have BE, but take care that in between you have a certain small air gap. So let's calculate the dimensions of every magnetic path length and then start calculating the or using our Ampere's law to get the different parameters we need, Hg, Bg, and Phi-g. I'm going to say firstly, I would like to get the average length of BAFE. BAFE. If you have a look here, guys, you will find that this is 2 centimeters. So from the middle point here, which is A, to the edge of this magnetic core, we have half of these 2 centimeters. So this is 1 centimeter from this part to that part, from A to this point. And you have another 1 from this point to that point. And you have 50 here in the middle. So we have now 52 between A and B. And it would be the same also for AF and FE. So we can say that the average length of BAFE is 3 times 52 millimeters. Sorry, centimeter. So this is 156 centimeters, which is 1.56 meters. So this is, you know, guys, in our relations, you have to use the length in meters. So you have to convert to meters by the end. So this is the length of BAFE, which is the same as the other length of the other reluctance, which is LBCDE. So this is equal 156 centimeters or 1.56 meters. So this is the average length of these two arms. For the middle arm, it's going to be now 52 centimeters minus our air gap length. So we can say LBE equals 52 centimeters minus 0.5 centimeters. So this is going to be 51.5 centimeter, which is 0.515 meter. So this is the length of the central arm. For sure, LG is 0.5 centimeters, so this is going to be 0.005 meters. So we can use LG in our relations. So these are the different lengths we have in this magnetic core. Now, we have the number of turns and the current. So the MMF is well known for both of sources. If you are going to make now Kirchhoff or loop or whatever the circuit analysis you would use, you can use any circuit analysis. So in this case, we can say, guys, that loop, if we make loop like that, moving, starting from here, moving like that. So this is a big loop, okay? In this case, we don't include the air gap. So actually, we need to get all the parameters in the air gap. So let's make another loop considering the air gap in our path. So let me use another color here. So what about using this loop? So we can make Kirchhoff for this loop here, for instance. So if I'm going to say this is phi 1, the flux moving here is phi 1, and this is phi 2, we expect that phi 1 and phi 2 will be equal. Why? Because of the symmetry of our core. So in this case, guys, we can say flux phi 1 will flow in this reluctance, BAFE, and the flux that will flow in the two middle or in the middle arm here is going to be 2 times phi, or phi 1 plus phi 2. So I can say here now, if I would like to write the relation, so I can say F1 equals reluctance BAFE times, so we are going to use now phi times reluctance. So I'm going to say times phi 1 plus the other two reluctances. So reluctance BE of the core plus reluctance gap all times flux in the central arm, which is phi 1 plus phi 2, which is going to be 2 times phi 1. Reluctances can be calculated. We have the dimensions now, the length of the magnetic path. We have the length of all reluctances. Cross-section area is already calculated here. We already calculate the cross-section area. So we can get the reluctance of every part. So reluctance, you know that reluctance equals L divided mu A. Mu is given, area is calculated, length is calculated, so we can get easily every reluctance in our circuit. And F1 is given. The only unknown in this relation would be phi 1, which is the flux. Now, the question is, if the flux in the air gap is the same as phi 1, or it's just half phi 1. Actually, flux in the air gap, which is in the central arm, equals 2 times phi 1. So after getting phi 1 here, we just need to multiply times 2 in order to get the flux in the air gap. So let's see the answer. So here, he start calculating the reluctance of BAFE, the left arm. So he said that 3 times 52 centimeters times 10 to power minus 2. So this is the length of the part BAFE, divide permeability of the core, which is 1200, times the absolute permeability, which is 4 pi times 10 to power minus 7, times the cross-section area, which is 4 centimeters square, so 4 times 10 to power minus 4. So this is the reluctance of the first arm. And he mentioned here, guys, the left and right arms C-shape reluctances are the same. And he calculates also the reluctance of the central arm. Okay, so 51.5 centimeters times 10 to power minus 2 divide mu r times mu node times cross-section area. So this is the reluctance of the central core. And the reluctance of the air gap is Lg, which is 0.5 millimeters, so 5 times 10 to power minus 3, divide mu node, because mu r of the air gap is 1, times the cross-section area again, which is 4 times 10 to power minus 4. So now we have all reluctances. So let's substitute in our relation. Here, guys, he said phi 1 plus reluctance BAFE plus reluctance BE plus reluctance G plus phi 2 times reluctance BE plus reluctance G equals F1. So he made now one relation for the first loop. He made another relation for the other loop. So he didn't solve the equations as we made. Actually, we assumed the symmetry from the beginning and we considered that, so it makes it easier. Okay. But here he calculated the values as if he doesn't have any symmetry. No problem. By the end, you would get two values. So you have now two equations, function of phi 1 and phi 2. And by the end, he got, in this solution, he got phi 1 equals phi 2 equals 2.067 times 10 to power minus 4 Weber. So again, guys, this is the textbook solution. If we go back a few slides here, so this is our solution. Both are fine and will provide the same answer. So after getting the amount of phi, again, phi in the air gap equals phi 1 plus phi 2. So this is going to be the amount of flux in the air gap. We got flux. Next step, we need to calculate the flux density. You know that flux density equals flux divide cross-section area. We know the cross-section area of the air gap, 4 square centimeters. So we can get BG, and also phi is going to be, sorry, H is going to be B divide mu in order to get the flux intensity. So here, this is the direct substitution in our relations here, guys. So this is BG. It's going to be 1.034 Tesla. And H, you know that we are calculating H for the air gap. So mu equals mu node only, because mu r for the air gap is 1. And we can get the Hg. If we would like to see, guys, this shape of magnetic core, what this magnetic core represents. Actually, we have some applications use some magnetic cores close to that. Okay, you know the kilowatt hour meter we have at homes. So the kilowatt hour meter, it will have air gap in between a magnetic core like that, and there is a rotating disk. So this is a conventional kilowatt hour meters. Okay, and this disk is rotating by means of the magnetic flux of the flowing in the core in order to calculate the electricity consumption. So this is one of the applications, but for sure the kilowatt hour meter magnetic core is very small compared to this huge magnetic core. This is 1.5 meters, so this is a huge core. Uh, we may have some huge cores like that without air gap, like in transformers. So for power transformers, the core can be huge and the current can be relatively high, and also the flux can be relatively high. Okay, and with this dimension of magnetic cores for transformer, the amount of power may reach to like maybe half megavolt ampere. So this is going to be a huge amount of power, not only for a 10 amp. This would be maybe like hundreds of ampere flowing in such a transformer with this dimension here. Okay, nice. Okay, one of the important things, guys, we have in magnetics is the inductance. You know that in electrical circuits, you used inductance in electrical circuits and you calculated the impedance and you had the transient analysis and you got that the inductance is a storage element, so it can store energy. Okay, so how the energy can be stored? Actually, the energy will be stored by means of having an air gap in the core. So if you have air gap in the core, so this means you can store energy in this core inductance. Okay. Also, we can use the inductance to limit the uh, current rate of change. Current rate of change. Rate of change means di by dt. So if you have high di by dt in any application, you can reduce the rate of change of current by inserting series inductance, because you know the relation between current and volt for an inductance is V equals L times di by dt. So if you would like to limit the di by dt, reduce the di by dt, simply you can increase the inductance in the circuit. This is the real inductance. Also, you may have what's called stray inductance. Stray inductance is not like a wound inductor, so it's not like you get some wire and magnetic core and start make winding with N turns. But in any electrical circuit, guys, because the current flow in any wire will create a flux around this wire. So there will be an equivalent stray inductance. It's like a virtual inductance. It's not a real inductance, but it has the effect of the inductance. But the virtual inductance or stray inductance is very small values in nanohenry or sometimes reach to small microhenries in our circuits. Okay, nice. So the inductance from the point of view of high power and magnetics, how can we create the inductance? As we mentioned, we got a core. We start make windings around this inductance in order to create the inductor. How can we measure the inductance in reality? We have what's called LC meter. So the LC meter, you can connect after creating the inductance, you can connect the LC meter to the two terminals of the inductor, flow the uh, signal of volt and current, and calculate the value or measure the value of the coil inductance and equivalent series resistance. So we measure through this device, we measure L and ESR. ESR is the equivalent series resistance of this inductance. Okay, guys? Okay, now we defined a parameter before, which is the flux linkage. So flux linkage is lambda equals N times phi. Phi is our magnetic flux lines in Weber, and N is the number of turns. What is the inductance relation as a function of lambda? L equals lambda divide I. So inductance equals lambda divide I. So we can say that inductance equals N phi divide I. And you know that phi, the flux, is nothing but flux density times area. So we can say it's N BA divide I. And you can replace B by means of mu and H, the flux intensity. So inductance equals N times mu times H times area divide current. Now, you know that I, you can get the equivalent of current from Ampere's law. You know that Ni equals H times L. So if you would like to replace I by means of this relation from Ampere's law, so you can replace I by HL divide N. So in this case, N would be moved to the numerator here, and the relation and H will be removed together, and you can move the mu and A to the denominator of the denominator. Okay, so we can say now it's N squared divide L divide mu A, and you know that L divide mu A is nothing but the reluctance of the core. So we can say by the end, inductance is equivalent to N squared divide reluctance. So this is the relation of the inductance. So if you would like to have high value of inductance, increase the number of turns, reduce the reluctance. And how can you reduce the reluctance? You can reduce the reluctance by means of, reluctance equals L divide mu A. So reducing reluctance means reduce the length of the magnetic path or increase the cross-section area of the magnetic path or increase the permeability of the magnetic core. And increasing the permeability of the magnetic core means select a proper magnetic material. Okay, so this is the way how can you control the reluctance of the magnetic core. So this is, guys, how to get a certain or make a certain inductance. Okay, let's see for one of our examples here. For the magnetic circuit shown in figure, this is figure 19, we have N of 400 turns and a core length, the average or mean core length is 50 centimeters. And the air gap we have here is 1 millimeter. And the cross-section area of the core or gap is 15 square centimeters. Consider a relative permeability of the core of 3 thousandths and a current of 1 ampere. Firstly, calculate the flux and flux density in the air gap. Actually, we already solved such parameters before. It's not related to the inductance. So very easy, guys. So start firstly with the reluctance calculation. So reluctance is nothing but L divide mu A. So we have the length, we have the permeability of the core, permeability of the air gap, and the cross-section area. So we could get the core reluctance. Also, the air gap reluctance, L gap divide mu node A. So we can get the reluctance. Now, we need to get the flux density. So let's get the flux firstly and then calculate the flux density. So we can say phi, according to Ampere's law, N times I equals phi times reluctance. And here we have two reluctances in our circuit. So this is reluctance total. So we can say this is phi times reluctance gap plus reluctance core. So substitute here in the relation to get the flux in the left-hand side. So it would be Ni divide summation of reluctances. So 400 turns times 1 ampere divide the summation of the reluctances of our core and air gap. So we can get the amount of flux. So the amount of flux would be 0.645 0.463 times 10 to power minus 4 Weber. Then we need to calculate the flux density, so we just need to divide over the cross-section area. So this is the flux density, it's 0.43 Tesla. Okay, this is part A. Part B, calculate the inductance of this coil. So you know that we just write the relation, the inductance equals N square divide reluctance. So we already have the equivalent reluctance of our circuit, the overall reluctance, okay, including both air gap and core. So we can say now the inductance equals N square divide summation of reluctances. So N square is 400 square divide total reluctance. So this would be the value of the inductance, 258 millihenry. 258 millihenry. By the way, guys, this value is very huge inductance. This inductance is very huge inductance. If we go back just one slide here, 50 centimeter average length. So if considering this average length like total 50, so this means we may have dimension of this one like maybe 1/4 of this 50, which is 12.5. So the dimension of this one could be like 15 centimeters by 15 centimeters. Okay, so this is relatively big inductor. Okay, and the reason of having this high value again is number of turns is 400. Number of turns is 400. Okay, so this is the value of our inductance we have right here. We can calculate the inductance by another means, like it's equals to flux linkage divide current. So flux linkage is N times phi. So phi is calculated 0.6 times 10 to power minus 3 Weber divide current, and N is given 400. So we can calculate the value of inductance by the same way. Okay, so this is just to know how to create inductance and how to calculate the inductance by means of the parameters we have in the magnetic circuits. Here we have another example. The coil in figure has 250 turns and is wound on a silicon sheet steel. So the magnetic core is silicon sheet steel. The inner and outer radii are 20 and 25 centimeters. So the inner radius is 20 centimeter and the outer radius is 25 centimeters. Actually, when we need to calculate the average length, we will not use either the inner or the outer. We have to use the average. So this means the average length would depend on the average radius R that we have here in this drawing. This can be calculated as the average. So we have 20 and 25, so it would be 22.5 centimeters. So R would be 22.5 centimeters, and we can get the radius of this average length by this way. Okay. Nice. Also, we can get the cross-section area by means of calculating the diameter of this toroid and then calculate the cross-section area in this path. Okay, what is needed here? The toroidal core has a circular cross-section. We mentioned that for a coil current of 2.5 amperes. So if the current, guys, is 2.5 ampere, find. Firstly, find the magnetic flux density. We need to get B. Add the mean radius of the toroid. For sure, when we calculate anything, guys, we calculate it in the middle or the average length path of the magnetic flux. So we need to get B in our toroid. In order to get B, again, let's write down the relation, Ampere's law, MMF Ni equals pi times reluctance equals H times L. Whatever term you need to use, you can use according to the data you have here. So we need to get B, and we can get B by means of phi or H and permeability, phi and the cross-section area, or H and permeability. So here in this example, the textbook answered this from the H and L term. So he mentioned here, guys, H equals Ni divide L. N and I are given. Length can be calculated as the perimeter of the circle, which is 2 pi times the average length. And the average length, we just mentioned, the radius of the average length is 22.5 centimeters. So he multiply here times 10 to power minus 2 to convert this to meters. And the amount of H is 442.3 ampere turn per meter. If you need the amount of magnetic flux density, you have two options. Either using the magnetic reluctance, the magnetic permeability, if it is given, or use the BH curve. Here, the permeability is not given. However, the material is defined. So the material here is mentioned, it's silicon sheet steel. So we can go to the silicon steel and get the value of BE corresponding to H equals 442. If you do that, guys, you will get the amount of flux density equals 1.225 Tesla. This is the first part. The second part, the inductance of the coil, calculate the inductance, assuming that the flux density within the core is uniform and equal to that of the mean radius. Actually, without mentioning all of that, we all of the time assume that the flux density, we assume that the flux is uniformly distributed around our core. This is the ideal case, but for, let's say, for undergrad level guys, all of the time we will assume the simple model of the magnetic circuits, okay? Otherwise, if you need to have detailed model, it's going to be a very complex model, and most probably we may end to use the finite elements methods or techniques of solution, or finite elements program like COMSOL, like Maxwell, like JMAG, all of these types of programs used for multiphysics and finite element calculations. However, for the undergrad level, we all of the time assume that the flux is uniformly distributed within our magnetic core. So now we need to get the inductance. So simply, guys, the inductance can be calculated by means of N squared divided reluctance. And in order to get reluctance, so again, inductance is N squared divided reluctance. And in order to get the reluctance, you need the core material. So reluctance equals L divided mu A. So the cross-section area can be calculated easily here. So the cross-section area can be calculated from the circular cross-section. So, you know, the area of circle is pi r square, and this radius can be calculated from the dimensions we have here. So the diameter is the outer minus inner radius. So 25 minus 20, and then divide over 2 in order to get the radius, and square it to substitute in the relation here. And by then, this is square centimeters, so you need to multiply times 10 to power minus 4 to get it in square meters. So this is the area of our core, and then you can say now flux equals B times A. Yeah, we don't have permeability here, guys. So since we don't have permeability here, we will use this one, or you can get the permeability at the operating point from the curve. So since we have the curve already and we have the operating point, so you can calculate the permeability from the first section right here. So this is another way. So here in the first solution, he considered that from the flux linkage. So he calculated firstly phi by means of B times A. So we already calculated B in the first part of the question. And so we have now lambda. And now after getting lambda, you can just divide over current in order to get the inductance value. The other way is, since you have B and H from the first part of the question, so you can calculate the permeability and calculate the reluctance, and then n squared divided reluctance, it would give the same value for your inductance. Okay, so this is how can we calculate inductance again for such a circuit. Now, we discussed it before, guys, the BH curve. How the BH curve is obtained for materials. And is there a different type of excitation? So the first discussion we mentioned was DC excitation when we apply a DC on a core. So this would be the shape of the curve that we had before. But if we have AC supply, will the relation or the curve between B and H will be positive only? Actually, no. What will happen is, if we have an AC supply like that, so with the current increase from 0 to the peak, you would have increase for the flux density with the flux intensity. Once the currents start moving from the peak to 0, we will not expect the current or the flux to return back to the same path. Why? Because actually there will be a residual flux in our core. Why, guys? So what happened? What's the meaning of creating magnetic flux? The material, guys, includes many particles inside. When you apply flux, the flux will start moving these particles. So in the beginning, these particles were not like uniformly distributed in the materials. Once you disconnect the supply, what will happen is these particles will not be returning back to its random position again. So what happened is, even if you disconnect the electricity or the flux from the magnetic material, you still have some residual flux inside. Why this residual flux exists? Because this material has been supplied before. So we expect that the once you return, you came to this point A, the flux density will not return back to 0 again. It will return back to a certain magnetic residual flux value. So this is called BR, or magnetic flux residual. And when the current go back to the negative, so it will continue direction, guys, until going to the negative side. So you would have negative B and H. Then moving to the other direction to the peak value, so it would increase again until returning back again, guys, to 0. Okay, so it would start from here for many cycles, guys, until having all the particles be uniformly distributed. And by the end, for many values of H and B, you would have some small loops or bigger loops. And the locus between the peaks, these peaks of these loops, guys, is called now the magnetization curve. So the relation between B and H, or the magnetization curve, is nothing but the peak values of the loops of the magnetic flux. This loop, guys, is called hysteresis loop. This loop is called hysteresis loop. Okay, so this is for the AC excitation. Nice. Now we have different types of cores, guys. So, guys, the magnetic material is not like any, they are different according to the BH curve. So, for instance, we mentioned that we have cast steel, we have cast iron, we have sheet steel. So, there are many materials, and every material will have different pH curve. So, if the value of H is relatively high, this would make high loss in the magnetic flux. So, by the way, the area, sorry, the area inside this loop, guys, is representing the loss in the magnetic material. So, the value of H here is relatively high if we go back to our problems. So, here, for instance, let's see the value of H in any question here. What is the value of H here? Yeah. So can you see, guys? H is 0.8 times 10 to power 6. So it's a huge value, okay? So we expect to have high loss inside the magnetic cores, except for some materials. Like what? Like the materials called delta max cores. So delta max cores are special ferromagnetic alloys, are sometimes developed for special applications. What are these applications, guys? Actually, this is the high frequency. Because for the high frequency application, the number of loops would be very much, too much loops. And if you have very high frequency, this would increase the magnetic loss a lot. So we do prefer to have delta max cores with very small value of H or flux intensity in order to reduce the magnetic losses inside the material. So these are some special materials, guys, used especially for high frequency. An alloy consisting of 50% iron and 50% nickel has a BH loop shown in figure below. So this is a composite of iron and nickel together. This can make very tiny material in terms of H, so very thin curve, BH curve. As you can see, this is just 10 ampere turn per meter. For sure, compared to the other materials we just discussed, it's very huge ampere turn per meter. So this is very small losses compared to the other materials. Okay. And by the way, guys, the cost of this material is very expensive because the losses of these materials are very small. So a coil wound on a delta max core can be used as a switch. Switch, we refer to switch, guys, for high frequency switches, like what we are using in power electronics and electronics. Okay, so this is preferred for the high frequency applications. Now, this is what we just discussed about the hysteresis loop, and the hysteresis loss is represented by the area inside the BH loop. So here, guys, for instance, if you would like to make calculation for the hysteresis loss, it's going to be the surface integration of the material here, of the BH loop here, which is the core volume. By the end, the energy is going to be the core volume times the integration from B1 to B2 for HDB until getting the complete integration for the inside pH loop in order to get the curve. I will not go more in deep, guys, in this in these relations, but I just need to discuss with you the last relation in the derivation. So this is what is important to me. Okay, so this is the BH. So what is BH? This is the hysteresis loss. So the hysteresis loss, guys, depends on the volume of core times energy per cycle, okay, times frequency. So frequency is very important, guys. Frequency is very important. So if you use high frequency, this power would be very high. For that, guys, in electrical machines, for instance, we have some drive system. You will learn that by the end of this class, by the end of the semester. We have something called variable frequency drives. So variable frequency drives try to reduce the harmonics and reduce the high order frequency waveforms in order to reduce the harmonics and reduce the losses of the hysteresis loss in the machine. So we expect that if you have AC motor, for instance, supplied by an inverter, the main frequency is going to be 60 hertz, but you will have some subharmonics and harmonics. So the harmonics can go up to several kilohertz. So the idea in power electronics, guys, we try to reduce these harmonics in order to reduce this type of losses in the electrical machines. For that, we care about the final relation here to just to understand what the meaning of hysteresis loss. So the hysteresis loss by the end depends on the WH, which is the energy density of the core of our material. V core is the volume of our core, and frequency is the supply frequency. There is another empirical equation. Okay, this is used for magnetic models, but this part is not important. Actually, guys, this part is for graduate students, but I just included this part here for you to just recognize the relation between the hysteresis loss and frequency, because we will need that sometimes in our course materials. Another type of loss, guys, we have in magnetics is called eddy current. So, you know, guys, current is flowing in wires for electricity. And if you have, for instance, if I have coil like that, and the current flowing here, this is AC current, and I have another coil which is open circuit, I'm expecting that the flux will move from the first coil to the second coil and will allow a current to flow here, because if you have like another short circuit or bath or something to flow the current, so firstly we will have induced volt on the coil, and this will allow a current to flow. This is for inductors and wires. But why not happening inside the core itself? So the core can be considered as infinite number of wires, because it's magnetic material, but it's conducting electricity as well. So since the flux is moving inside the core, it will interact internally in the core and flow a current. This current is called the eddy current. This eddy current, guys, is making another part of loss called eddy current loss. And the relation of this eddy current loss is frequency dependent also, and it depends on F square. So the higher the frequency, the higher the eddy current loss in our material. How can we reduce this eddy current loss? The way to reduce the eddy current loss is to make separation between the core parts. So if I have a complex core like that, instead of having just one core, I do prefer to make these core parts made of many sheets connected together. And between every sheet, we'll have some insulating material. So the insulating material will prevent the electrical current to move from a sheet to another sheet. So this is the concept now. So we made insulator between these sheets in order to reduce the eddy current loss. For that, and we didn't comment that in the example, if we go back few slides here, you will find one of the examples here mention that this coil is made of wound on silicon sheet steel. It's not silicon steel. So sheets because we made the core of sheets and we make insulation between every sheet in order to reduce the eddy current loss inside the magnetic cores. Okay, so this is what's called eddy current loss. The summation of the eddy current loss and the hysteresis loss is called core losses. Core losses. So by the end, guys, this is the core loss. Core loss equals PH hysteresis plus P eddy current loss. Okay, this is just to know what the meaning of core loss, guys. So the core loss consists of two parts: hysteresis current and eddy current loss. Sorry, hysteresis loss and eddy current loss. And recently, we figured out in magnetic research that there is a third part called excess loss. This excess loss term comes because of the polychronic converters used. So these are the different parts of the core losses. And again, the last part is just to know about something about the core loss, but it's not going to be considered for questions or numerical questions in our exams. This is just to know that the core loss has two main parts: hysteresis loss, eddy current loss. How can we reduce eddy current loss? We can reduce eddy current loss by means of creating insulated sheets cores, not solid cores. Okay, so this is everything we need to cover in magnetics in order to understand the remaining topics in our class. So we are ready to start in the next class in the transformer topics. We understood now everything about magnetic parts. So in the next session, we will start together in power transformers. By the way, guys, I'd like to remind you this Monday we have lab session, or we had lab session this month, the previous Monday, and we will continue our lab sessions in the coming Monday. Thank you so much, and have a nice evening.